Welcome to another episode of the Mapscaping podcast. My name is Daniel and this is a podcast for the geospatial community. Today on the show we're talking about synthetic data, and so this is not the synthetic you think about when you think about synthetic aperture radar. This is the synthetic we think about when we think about fake, not real, generated, that kind of synthetic data. Here's a little bit of background before we jump into the conversation. Computer vision is everywhere, but teaching an algorithm to identify objects requires a lot of data, and this is definitely the case when we think about GeoAI. But it's not enough that we need a lot of data. We also need that data to be labeled. So, for example, if we're looking for cars and images, we need a lot of images of cars, and we need to know which pixels are the car. Of course, I'm oversimplifying things here, but I hope you get the idea. Now imagine that you can automatically generate a large label data set of realistic images of cars based on the specifications of a specific sensor. These data sets are often referred to as being synthetic or fake data, and to help us understand more about this, I've invited Chris Andrews from Rendered AI on the podcast. So this episode is building off a bunch of different episodes that we've published before around computer vision, and there will be a few interesting links for you in the show notes today that are well worth checking out. Before we get started, a big thank you to the Open Geospatial Consortium, the OGC, for inviting me to their members meeting in Alabama and for helping make this episode possible. Thanks very much. I really appreciate your support. Hey Chris, welcome to the podcast. We met a while ago now, a couple of months ago at an OGC meeting, and you're doing something amazing, at least in my mind. You're creating synthetic data. You work for a company called Rendered AI, and I've been wanting to have this conversation for quite some time. Before we get into the synthetic data stuff, maybe you could just tell us a little bit more about yourself, perhaps like a brief introduction is what I'm looking for. Who are you? How did you get involved in this? And what is your title at Rendered AI?
Yeah, thanks, Dan. I appreciate the chance to chat with you. It was a lot of fun to take a walk with you and chat a couple of different times in the sun in Alabama there at the OGC meeting. I'm definitely happy to share a bit about what we do and who I am. So my background is I started off in the sciences, in geology and ecology. Along the way, I was always a programmer, and then somewhere in my graduate work, I was directed toward GIS because I had kind of built my own mini GIS to map out ant populations. And that actually started me working with. I got interested in ArcView, so the original ArcView. I think it was actually 2.0 or something like that. And when I actually sat down at it for the first time, I actually started programming. I think there had just been an update to ArcView, the Avenue programming language. And so from the very beginning, I was always interested in customizing, extending GIS for analytical and other purposes, not so much cartography or the kind of map production side of GIS. So starting to work in GIS brought together some of my interests around data investigation and analysis, and then visual stuff. I've always liked to work in visual domains. That's why I've been in GIS or GIS centric things for so much of my career. And from there, having an ecology degree in the mid 90s was not such a great thing. And so in terms of for jobs, but having some programming and GIS skills was a fantastic thing. It got me job offers at startups and at bigger companies like Bentley Systems within a couple of weeks of graduation. I'm pretty sure I was one of the first people to put a map on the web. I think there might have been people who did it earlier, but this was an interactive map that you could zoom in on and pan around on it. From there, that got me into more web mapping stuff. And then from there, a stint at the Kennedy Space Center and work in enterprise integration, which then took over the next few years of my career. I eventually ended up picking up a variety of specialty around utilities and AEC. And then I ended up at Autodesk. After 7 years at Autodesk, leaving, and then less than a year later going to Esri, where I started out as the product manager for 3D across the ArcGIS platform. that was an
Wow.
interesting opportunity because it allowed me to touch just about anything, right? My joke used to be people would ask me about different things, and I'd say, "Well, gosh, I don't know who's the 2D product manager here." And the reason why that's kind of an inside joke is because really it's Jack Dangerman, right? He's the
Yeah, yeah.
ultimately the arbiter of all that, and so it was an interesting opportunity to kind of carve out a new role that touched just about everything. So it was a pretty interesting role. I almost immediately helped get the ArcGIS Earth effort started. Theo Radulopoulos at Autodesk and I got together and we helped get the Autodesk Esri partnership started. That was a huge effort to convince Esri that BIM was really relevant to GIS, and now it's a deeply established part of their market very rapidly. So that was all fantastic. I ended up after 7 years being one of the PM leads. I had a team of 20, and there were about 45-ish products under me. But I kind of wanted to get back to my smaller company roots and have a bit more direct influence on the development of a small company in an emerging technology domain. And not that there was, everything was completed in 3D and BIM GIS integration, but I've always leaned into these new areas. And so, opportunity came up to join a small company who is working on synthetic computer vision imagery for AI training. And this particular company happened to do a lot of their initial work in the remote sensing space, simulating satellite imagery. So it kind of brought together my interest in contributing at an exec level at a small company to help build and grow a business and market, and then also background in everything from 3D to digital twins to reality capture, simulation, and then still is quite open beyond that because computer vision is everywhere across just about every human industry these days, and it's just starting. So there's tremendous opportunity. I ended up joining Rendered AI as the COO and head of product, and that was about 2 years ago. And we've been continuously and steadily growing and expanding our business since then, and it's been a quite exciting adventure so far.
Wow, you have come a long way. So a couple of key points I just want to sort of highlight here. You started off, writing your own software, building your own GIS to map ants. You were one of the first people to put a web map, to create a web map, to put a map on the web, which is amazing in itself. You worked at some massive companies. It sounds like you've been on the forefront of a lot of technologies, as they were emerging. So 3D, like I remember back in the day when I started a GIS, the joke was it's all flat. Like if you want to do 3D, if you want to actually model the world, then you need to go to BIM because over there, they're into 3D. You guys are still flatlanders. It sounds like you're on the forefront of that, at least at Esri. And now you're working with synthetic data. You're getting back to this. I think you called it your small company startup roots again. So let's dive into this synthetic data thing because that's the promise of this episode is to help people understand more about it. A while ago, I published an episode called Fake Satellite Data, and it was all about using GANs, so generative adversarial networks, to produce fake imagery. Is that what we're talking about when we talk about synthetic images or synthetic data?
No. Before I address that directly, I just want to want to tell you an anecdote about myself in 3D. So the actual first 3D map that I ever built was I hand surveyed an ant field in Tallahassee, Florida, in 1996. So I used a Brunton compass, a geology tool, and a 1.5 meter stick to basically build a 3D map of the entire meter by meter at a 1 meter resolution for this entire 50-meter radius ant field and study field. And then I actually used Excel to plot it as a bunch of 3D points. So
Wow.
that was my first brush with 3D. And then later I actually did touch 3D Analyst about 2 years later when I was with a different startup company from the first one. So I don't know. I always had a nose for leaning into technologies that were likely to take off, and avoiding some that were not. For example, I avoided cold fusion and PHP like they were the plague because I just looked at them and said, these are not going to stick around. And you could say that they kind of have, because there's a lot of like zombie apps out there that are still based upon both of them, actually, frighteningly enough. But I've just had a nose for it more on the tech side than the business side. I guess if I'd had more of a nose for it on the business side, I'd have a few extra zeros at the end of my bank statements, but I don't. Back to your question. As I said, we focus on synthetic computer vision data. Actually, what we build is a platform as a service for customers to generate tailored synthetic computer vision data for training algorithms. We don't do algorithm training, and in some cases, we don't even need to help customers with the process of setting up their synthetic data simulations. And we can talk about that. Today, all of the synthetic data channels, which we call synthetic data applications, a synthetic data channel, all of the synthetic data channels that run unrendered today are not GAN based. There is a step where we can use GANs, and I can come to that. But so today, what all of the simulations that we run do is essentially use kind of classical simulation techniques to emulate physical processes in digital form and then simulate the collection of real sensor imagery. And this is true for, we have customers who have channels for RGB and panchromatic satellite imagery. We work with DeerSig from RIT, that is a long-term government-funded simulator for multispectral and hyperspectral imagery. We have our own SAR, synthetic aperture radar simulator, and all of those things are physics-based simulation systems. And so we don't actually use GANs to generate the primary imagery that a customer might be interested in. Entirely conceivable that in the future, or even next week, that we could build, or a customer could actually build in a GAN into a synthetic data channel in rendered AI and start generating synthetic computer vision imagery using a GAN, or something in one of these diffusion models. However, there are today some major differences between physics-derived synthetic data versus generative AI-derived synthetic data that would make that generative AI data less usable than physics-based synthetic data.
Okay, so let's talk about the physics-based synthetic data that you are creating, or your customers are creating on your service. What do I start with? What do I need to get going with this?
There are two parts to our platform. One part, every platform as a service out there is all about hiding the complexity of cloud capability to accomplish some kind of job. And the job for us, the job that our customers need accomplished, is to get lots of fully labeled computer vision imagery out of this process that is effectively magic to most data scientists who today rely on real sensor data collection. On top of the platform is this notion of these containerized synthetic data channels. And so by containerized, what I mean is we literally use Docker. Docker is a technology product set for building these packages, wrappers around a self-contained programming programs of some kind. Docker is used for many, many things, not just synthetic data generation. In our platform, we provide a framework to basically construct one of these Docker containers to have some simulation capability, so a renderer of some kind. This could be NVIDIA Omniverse or DeerSig or conceivably Blender, or we've had experiments with Unreal Engine, for example, as well. And then access to content to be able to assemble a digital twin of a scene, a real, simulating a real scene somewhere that you might point a sensor at. then some sensor parameterization, and then other diversity that can be introduced to that simulation. For example, do you need fog effects or variable lens distortion or variable like daylighting or anything like that? Basically, that this containerized simulation packages up access to 3D and 2D content, the simulation capability itself, parameterization around the simulation, and then that container can be deployed to our platform. And then a data scientist or computer vision engineer can use a very simple web interface to configure the actual jobs that will be executed using that simulation. And then the platform is there so that when the computer vision engineer pushes a button and says go, they can get 10 or 100 or 10,000 runs of that simulation. And as I hinted at a second ago, in that simulation is built in variability that can be stochastically varied, such that, if you're looking for zebras, you're trying to build an algorithm to count zebras on a grassy plain. Well, part of the structure of that simulation includes information about how to place zebras, how many zebras could be placed, and then even where against the background that the zebras would occur. So that when you run that simulation 10,000 times, you'll get 10,000 image chips with the zebras in different patterns according to your parameters on those image chips. And then you'll also get annotation identifying things like bounding boxes around the zebras. And then for RGB and a few other data sets, you'll also get pixel image masks, because when you're rendering that image, you actually know what is at each pixel. So I know where the zebras are. I know where the grass is. I might know where the river is if I had a river in there and I care about it. That's something that you can't get through generative AI today, not directly. In the generative AI world today, we're typically talking about, a text instruction that is interpreted through some kind of vector database, and then that information that is then extracted from the text instruction is used to drive the generation of the image in whatever generative model is used to spit out a set of pixels at the end. But those pixels are not deterministically prescribed in that model, such that you don't know where the zebras are in the image. You just happen to know that there are zebras against grass in an image spit out by that generative model.
We cover a lot of ground there. Let me try and summarize this a little bit, and you can tell me where I'm going wrong. So my understanding is this: you keep calling it containerization. We have this container. Inside the container, we have a model. I think you referred to this as being the content. What is it that we want to simulate here? So in your example, again, it was a zebra. So I have a physical model of a zebra. At least this is my understanding. And in this container, I have parameters. So I can say, oh, I'm using this kind of sensor. It's going to be this. The look angle is from this side, from this height, from this angle, or whatever.
Yep.
Maybe I need some fog or something like this, and I can say, okay, as the data scientist, generate, run, and this container, this program will go off and create maybe 10,000 images of zebras, given the parameters, given the scene that I have described that I wanted to take images of. And in those images, I not only do I know that there is a zebra somewhere in this image, but I know which pixels are the zebras. So not just the bounding box of the zebras, but which pixels are the zebras. And my guess is this would be an amazing training set. If, for example, maybe I don't have time to wait for all of those to build up a massive training set of satellite imagery where I know that I have zebras in it because of clouds, because of the passover rates, whatever, because of the orbits, because maybe it's really difficult to find zebras. This sounds like a way of generating such a training set.
That's exactly right. And then there are a few other questions that come out of that. For example, are my pixels, is it really like real imagery collection? And we provide a couple different techniques to help both post-process the simulated imagery to be more like a real data set, and then also to compare data sets to make sure that the synthetic data is going to behave as if it is real data to when training an algorithm. So there's more to it than just kind of this containerized digital twin of the sensor collection scenario. That's part of it. And after that, then you may do things like actually use a cycle GAN that's been trained on real sensor data to post process the synthetic data to make it kind of look to an AI more like the real data. And then beyond that, like I said, there is this opportunity to then start comparing real and synthetic data sets and actually exploring if you make changes to your synthetic data, does it actually make it appear more like real data to an algorithm? And that's another nuance is suppose you generate one data set with zebras in one particular pattern, but then your research comes back and you decide that, you know what, zebras actually, the way they follow each other or the way they stand around looking at each other actually is in some other patterns than what was built into the original simulation. Or suppose you want to mix zebras and buffaloes and make sure that you're not accidentally counting water buffaloes. Well, you just go back to your synthetic data channel. You configure an additional. You maybe add in some more 3D models. You configure an additional run, and you kick off 10,000 more images. And it's really that easy once that channel is set up to experiment with a wide variety of data variation. And suppose you want to make sure that the algorithm is going to fail predictably. And one thing you can do, for example, is you could go in and you could say, I want all my zebras to be blue, knowing full well that zebras are never blue in the wild. And in that case, you just basically add in a modifier node, is what we call it, in the graph interface that you use to configure synthetic data runs, and you'd say, I want my zebras, but I want them all to be blue. And you kick off the job, you generate 10,000 more images of blue zebras standing around a grassy field. And then you go and see if your detection algorithm works or fails as you would expect it to against those images. There's a ton of opportunity to explore with algorithm training and validation verification once you have that initial synthetic data channel set up and you have the right pipeline in place to assure yourself that the synthetic data is performing as if it was real data during algorithm training.
This is a slightly off topic a little bit here, but it's like I get this idea of creating these training sets and how we can change and adapt and test and retest and redo things. This makes a lot of sense to me. Has anybody shown up and said, "Hey, I'd like to do this to see what kind of sensor we should build. Here is a scene that we're interested in capturing. What is the best possible sensor?" And then just adjusting the parameters of the sensor inside the model and rerunning it and figuring out like how is our sensor going to perform over the scene? How can we tweak the sensor before we even build it, like to collect the best possible data?
That's a fantastic question, and is it's very close to one of the common use cases for rendered AI today. You might say that people who build hardware today do use a lot of simulation tools like ANSYS tools, things like that, to try to do engineering design and refinement. We, our platform typically comes into play after that engineering design step when somebody has settled on a sensor that they want to build, and then they want to generate a bunch of simulated imagery from it to prove that they can do AI training. So you're hitting on an important distinction between simulation for engineering design versus simulation for AI training. It's entirely possible down the road that, and those things are already merging, right? There's been, Autodesk did a lot of work with early work with generative AI. I'm talking 10 years ago. They actually built cloud based products that would do things like optimize the shape and form and volume of structural parts in chairs and race cars, motorcycles, so that you could get out of this algorithmic pipeline an optimized part that is as light as possible, uses as little material as possible, and but is still as strong as possible given your parameters. That's a type of synthetic data. We have not been used for that, but we absolutely, I'd say half of our customers are using us to prove out algorithm training on future systems that may not actually yet be deployed in the field. So, and that's true for satellite systems, drone systems, vehicle mounted systems. That idea that I need data to innovate is definitely one of the key use cases that we are used for today.
So when we talk about physical models, could you just explain this idea to me, please? Is it enough just to have the extremely accurate dimensions of the object that we're trying to model, or do we also need to know about the materials being used? And my thought process is here is it's one thing, at least in my mind, to identify an object. It's another thing to simulate the reflection level at different wavelengths. So when we talk about these models, are we looking for an accurate shape, or are we also looking to understand the materials used within the models?
Great question. So, when a customer is building a synthetic data channel in rendered AI, they are trying to emulate some kind of real sensor data, for one thing, and then also real world conditions for collection of that sensor data. The sensor itself may actually determine how much information you really need on that 3D model. So, if you are doing a nadir satellite imagery of elephants and zebras on a plane with 1 meter resolution, you probably don't need the same kind of materials reflectance information that you want if you're simulating a SAR collection of that same scene. It really ends up depending upon the sensor domain and kind of the collection regime that you're working on. There are some really hard cases like infrared. The way that infrared bounces off of water depends greatly on the wavelength of infrared that you're trying to collect. And if you are trying to accurately simulate a scene in rendered using, on water, using a sensor simulating infrared, then you're going to need to have scene elements that have the right properties so that you can simulate the right physical effects. Obviously, the RGB simple lighting cases, of which there are lots out there, they are the most easy for us to address. Nathan Quince, the primary founder of Rendered, he is a physicist with a background in general relativity and electric materials. So he founded the company under the premise that the data that we simulate needs to be physically accurate.
Great. Thank you very much. Appreciate that. Do you feel like that the trend around reality capture, digital twins, we seem to use these terms everywhere now, not just in terms of buildings, but in terms of scenes, in terms of much smaller objects as well, or in entire cities. Is this in any way accelerated, like the ability to create these synthetic data sets? And my thinking is here: the more accurate models we have of the world, the more we can do this thing that you're talking about. The more perhaps we can take these similar models, use similar techniques to capture reality and put them into a system like yours.
There's opportunity there. I'd say in many cases that is ahead of the market today. And it's not that there aren't people doing what you're saying. I think the synthetic data market is kind of bimodal, as most technology markets are when they're starting out. You have some big, deep pocketed organizations who have a lot of money to invest in synthetic data development. And there are those today like Waymo, Tesla, Apple, Amazon has a synthetic data pipeline for training drone data delivery, for example. In that case, those groups are using sophisticated content pipelines to kind of infuse content into the simulation. And then they're also using highly specific, highly tailored simulation models that say, emulate the exact parameters of the sensors that they're going to use on their cars or trucks or drones or whatever it is. And then they're also, they're feeding that data into a highly bespoke AI training pipeline because they are trying to accomplish some really hard but huge potential market opportunity problem, like self-driving cars or trucks or automated drone delivery of packages, that kind of thing. So that's there, and those folks I think have benefited tremendously from at least concepts, but also implementation around reality capture and kind of this not just static, but mostly static digital twinning of the real world. In the medium and longer tail of the market, one of the reasons for the founding of Rendered is because most companies out there don't have the deep pockets of a Waymo or Tesla or somebody like that. So if I'm a 200 person agricultural startup that is well funded, has profitable business, but needs to get ahead by training computer vision algorithms to do things like detect disease or damage to crops or something like that, or maybe optimize pesticide spraying, then I probably can't afford the full stack of stuff that Waymo or Tesla can afford. And there's no real option out there for me today. And that's where Rendered comes into play, because we hide a lot of that complexity. In those cases, in that we not only hide the complexity, we also help mitigate some of the cost of setup and maintenance of that cloud infrastructure to support dataset generation. What I'd also say about that middle and longer tail of the market is that their needs are often less sophisticated than the needs of somebody trying to train self-driving cars to be much, much, much better safety-wise than a human driver, right? So you're in a orders of magnitude different, higher complexity problem set in those big companies that have built their own synthetic data capability. Amazon, they don't want to deliver packages to the wrong addresses. They also don't want to deliver those packages to the wrong place at those addresses, and they don't want to drop packages on people's heads or on people's cars. So the problems that the big folks are solving require much more sophistication around digital twinning the real world and making it a dynamic simulation playground for training AI than the middle and longer tail of the market that we are trying to serve. We're happy to work with those folks too, but they've got tons of deep investment in their specific problem set. What we tend to see today is the state of the market is a lot more people are kind of just discovering computer vision, trying to tackle basic computer vision problems. And then they run into issues where they either can't get data, it's too expensive for them, it doesn't have the right diversity of problems in it. Like you can get lots of pictures of strawberries, but can you get enough pictures of strawberries with a particular kind of blight or damage or insect or something like that? So we tend to be in a space that is somewhat less sophisticated digital twin wise. But yeah, all the developments from everybody from Epic Games to Esri, Bentley Systems, Hexagon, Autodesk, all of those companies are fueling commoditization of capability to capture the real world at many different resolutions, both in time and space. Then they're all of that interest is driving increased focus on standards to kind of be able to make all that data more usable across many more use cases. And so we're seeing the evolution of things like, there was just announced this OpenUSD consortium around universal scene description that was originally started by Pixar and Autodesk and a few others. And now they're, NVIDIA and others are really investing in it as an open format for sharing 3D content around all kinds of applications, from games to simulations to you name it. So yeah, the digital twin world has definitely influenced the ability to generate synthetic data kind of from a fundamental technology perspective. I'd say if you were actually to look at a pipeline developing or creating synthetic data today, if you go into one of those big shops that is kind of DIY'd their synthetic data pipeline, you'd probably look at that and see that as much more of a digital twin of their problem set than you would many of our customers.
Right. So if we get back to sort of your sweet spot, your customers, we talked about. It sounded like we're talking about almost discrete objects. We talked about as opposed to a scene, an urban landscape. We talked about strawberries. We talked about zebras, that kind of thing. Does this replace or does it augment things like manual labeling and ground truthing?
Before I go on to that, so yes, many of our customers are focused on discrete objects. At that same time, we are helping them simulate real sensor data capture. So that may mean in some cases that we are building out digital versions of real environments. It is usually more sophisticated than just an isolated object in space. In terms of replacing manual labeling or ground truthing, it is not always a replacement for it. They're kind of two broad categories that I run into when I listen to customers' needs. One is customers who are looking for warm hits. They have an idea on training an algorithm. They can describe kind of what they want to look for. They may even have some 3D models of what they're trying to look for or some other information. But they just can't get enough data today, manually labeled or not. And so they need more data to kind of supplement that process of algorithm training. We have many of our customers have been quite successful at kind of jump starting in that way. And actually, a couple of different partners and customers have shown that the optimum results can really be achieved through a combination of using some real labeled, manually labeled imagery, and then also synthetic data at the same time. So I wouldn't say it's a complete replacement. On the other side, the other kind of group of customers are customers that are looking to kind of fine tune the precision of some kind of established model. So this happens in manufacturing and a few other areas where they're constantly looking at the same objects, but they're trying to tune models to recognize really rare defects or defects is a common one or counting things and need high precision. For that, synthetic data alone is definitely not going to get you to that tuned performance. Typically what we see is that in those cases customers have to have some real manually labeled data. They can then supplement it with synthetic data. And we have one partner, for example, that has demonstrated that they create a type of synthetic data from just simple reality capture technology where they take images of real parts and then image or generate a 3D model of those. They were able to prove that by simulating imagery off of those kind of static reality capture examples, they can actually better identify defects. And then they worked with us to actually use our platform to introduce more variety into defects, and they were able to show yet another performance jump once they introduced synthetic data with stochastic variability. So, in reality, to get to high precision use cases, improve accuracy incrementally, what you'll see is some combination of real and different types of synthetic data come into play.
What's some of the stranger use cases you've seen for this?
So actually, most of the use cases that we service are have a lot of real world impact. For example, helping detect generating greater diversity in damage to train parts to improve algorithms looking for inspection algorithms looking for defects and damage on in-service trains that like that has real impact. There are 1,000 derailments a year in the U.S. Quite a few military and defense use cases where you're looking for rare and unusual objects in the field in different locations. We've got a medical customer looking at trying to increase diversity around imagery to do detection of a certain skin condition through a mobile app. So a lot of our customers actually have real important real world applications of computer vision. We've talked to some amusing ones. One of the more amusing ones was one of the robot vacuum makers, they actually have difficulty getting enough imagery of dog poop in, on living room floors, that kind of thing.
Oh.
We did a project for a defense contractor, and they were using us to simulate a marine imagery. And apparently, in some parts of the world, dead animals are commonly found floating in the water, in the ocean. And they wanted to be sure to, one of their concerns was that they didn't want to be accidentally detecting the dead animals, as they wanted to detect something else. So, there's quite a lot of oddball computer vision use cases. We've all seen like images of, say, Tesla's pipeline or something like that, where they're simulating ostriches running across the street in San Francisco or something like that. You could actually point to the recent failures around some of the automated taxi in San Francisco as somebody's failure of imagination around their synthetic data pipeline. Because what was happening, I'm not sure if you saw the articles, is that locals are getting frustrated over these taxis, and they've been able to disable them by simply placing a traffic cone on the hood of the car, this automated car. That's something that, yeah, the car should raise a flag, should send a warning to the system operators if there's a traffic cone been placed on my hood. But should it really be impeding the full operation of that car? Probably not. And there are some frightening implications of like the car not working if other things like that happen that might be more dangerous. So the options for, if you're just using real sensor data, then your imagination around what you might need to train for is going to be bound by what you think you can get in real sensor data. One of the challenges that we have is sometimes backing our customer up from the point at which they usually start, which is getting that real sensor data, and instead getting them to talk through the full range of and think through the full range of possibility around what they really should be training for to support whatever business outcome they're looking for. And so, you can think of it as kind of almost a scientific method process, where what you really want your customer to do is kind of describe the ideal data set or data sets that they would need to train their algorithms. And that's their starting hypothesis. And then we can help them, rendered AI can help them generate data to support that hypothesis and test it. What we almost always find is that from there, the customer needs to back up and say, well, you know what, our assumptions weren't right. We need to change the data that we're generating and generate more data. So it's been really fascinating to see how customers start to change their mindset once they have this ability to just generate an unlimited amount of synthetic computer vision content.
Yeah, like when you talked about that, being able to disable a autonomous vehicle by putting a traffic cone on the hood of it, it made me think. Well, where do you stop, for example? So in that scenario, if we start heading down that path, then anything's possible, and it seems like an impossible task to train for every conceivable and inconceivable situation. And this must be a similar problem that your customers are facing. Where do we stop? If you can train for everything, should you do it? Because I mean, it's impossible. But where do you draw the line?
Yeah, that's a deeper AI ethics type question, and it's gonna depend on the domain as well, right? If you're building an AI to enable some kind of game, tabletop game or computer game, that's different from building a healthcare detection algorithm, which is different from building, a flight safety mechanism and algorithm. So it really is going to depend somewhat on the use case. At one, it might have been at the OGC talk. I think I described that really what we're talking about doing today is something that we've been doing for a long time. Since the dawn of the ledger, we've used math to support decision making. So, even going back hundreds of years, a ledger and some basic math tools were you could think of those as decision support tools. What we've done in the last few years is exponentially level up decision support and move decision support closer to the end decision making, like inflection point. So we're now relying on, instead of humans looking at pixels and counting zebras, we're now able to increasingly rely on an algorithm to count zebras and maybe even make some inference about the specific activity the zebras are engaged in across a whole bunch of images. At the end of the day, though, there's a human who is probably making some decision based upon that information that's being extracted at that point. A couple of years ago, or actually and still in practice today, earlier in that decision support tooling, there would have also been human decisions to say, yeah, I think these are zebras standing around, these are zebras drinking, these are zebras, on the hoof in a migration. What we're talking about is gradually reducing the amount of human effort in all of that inference so that we can get to more decision making. The hope is that you're not just turning a bunch of naive decision making over to an automated system. And that's where the diversity of training information is really going to depend upon the criticality of the domain. So for self-driving cars and medical applications, there in one sense there isn't an end, but there, if you listen to I listened to an interview from Elon Musk a few years ago, and he was talking about trying to improve on vehicle safety by, I think it was like an order of magnitude better than humans in terms of avoiding accidents and death and injury. And so that maybe is therein lies the answer to your question, really, which is if you're going to really move beyond decision support and into decision making, what is the threshold that you need to feel that the algorithm performs at that's better than humans to be able to trust it? And from there, you get into the question of, okay, well, what is the data set diversity that's going to be required in order to train the algorithm to that level? And so that's a long-winded way of saying it, but it's a much more nuanced answer than would seem, because it really just depends on the nature of the computer vision application.
You tied it together so beautifully at the end there that what are we trying to do? Are we trying to move beyond decision support to decision making? Okay, so what needs to happen? At what level are we comfortable handing over the reins, kind of thing? I think that was a really brilliant way of describing it. And yeah, of course, we ended up with, yeah, it depends on the situation, which also makes a lot of sense.
Sure.
So I'm a firm believer that nothing is for everyone. In what situations would you turn down customers, turn down work, say, hey, I understand what you're trying to do, but this synthetic data is not for you. Who shouldn't be thinking about synthetic data for their to create data for their computer vision applications?
I guess one area that we definitely would avoid is there have been a few kind of human monitoring detection use cases brought to us that are ethically questionable around things like generating diversity of people looking at different ethnicities for certain types of decision making that we just would stay away from, because we don't want to be involved with the end outcome of that algorithm training. There's probably a few other cases like that, but the other place that I'd say we would probably avoid is on that engineering optimization kind of novel simulation side of things. It's just a different problem set from synthetic data emulating real world scenarios for training detection. And there's a lot of prior art that has already been invested by Autodesk, Dassault System, Ansys, and others into that simulation optimization for engineering and product design kind of thing. So we would stay away from that. beyond that, it's there's so much computer vision that's being applied everywhere. I mean, everything's being sensorized, right? Microelectronics is a thing where you've got pinhead cameras being installed in light bulbs above your head in retail stores all around the world and things like that. There's so much computer vision that is going to be done in the future. The opportunity for us to work with customers is really endless. An example is I was at a conference last fall where there was a group talking about this kind of point of sale human observation system to make sure that people were being charged for things they were carrying out of a store. And they said they were using off the shelf trained backbones that often missed things like when a human had a scarf around their neck or was wearing a ski jacket of a particular type or other things. And so, you can see that in many cases, back to your other question, there really isn't an end to the amount of diversity that you need in simulated or real sensor data to train algorithms. You kind of have to call the end to generating and using data when you've satisfied the business model objective or the other detection objectives that you need for that particular training. But in the case of the ski jackets and scarves, you really want to be able to detect that people are carrying chocolate bars out of a store in the winter just like you do in the summer. So that's that's a legit use case where rather than standing up a bunch of people and taking pictures of them in scarves and ski jackets, you could actually simulate a lot of that and train algorithms. So it's quite diverse. There are definitely cases we would not touch, but there is 99.9999% of stuff that we see is well within scope of what synthetic data could be used for.
So, given this sensorization of the entire world, and cameras are a big part of this. So we're not just talking about sensors that are detecting air temperature or something like that. We're talking about visual sensors, sensors that are taking pictures,
Yeah.
collecting film, that kind of thing. Given that, and my guess is like you that this is only going to increase dramatically over time. What do you think the landscape of synthetic data is going to look like in the future? Let's say the next 5 years. How are things going to change from the way they are today?
One quick distinction to call out is that there are really two branches of synthetic data, and we've focused on computer vision and imagery, which also can touch video and LiDAR and things like that. That is where rendered operates. There's a whole other branch of synthetic data that is focused on NLP, text, form data, that kind of stuff. And we don't really play there today. There are other companies that are more established in that space, and it's actually high. I'd say that the barriers to entry are lower than the computer vision side, so it's been an area with more entrants quick. The market will grow. There's a bright analyst in, I think, Germany named Elise DeVoe who actually tracks the synthetic data market. And in her reports, what you can see is that the number of companies out there offering synthetic data has tripled in the last 2 years. I think it's 2 years. So, and what we're seeing is really what I've seen multiple times in my career, which is the start on a market explosion into and what will become an essential technology component in this AI world that we're all confronted with. Over the next 5 years, one of the things that is absolutely going to change the way that we provide synthetic data will be generative AI. And back to what I said earlier, today, generative AI is not ideal for generating whole image chips, but we can already see advancements like text to 3D model and kind of infinite texture development out of generative AI and other things that can be used as part of a synthetic data, like the simulation and scene assembly part of synthetic data generation. So it's entirely conceivable that in, I don't know, 5, 10 years, however long, that you might be able to actually speak the scenarios that you're trying to generate and actually get out of a rendered could get to the point where you could get an auto-constructed synthetic data channel and then start generating data from some kind of text to synthetic data experience. We're not there yet today, and there's a lot more kind of infrastructure and scaffolding to be built before we get there. But that's one place where the synthetic data, computer vision synthetic data market is definitely going to change. There are already some synthetic computer vision data providers using generative AI. They tend to be in more fixed domains, so say vehicle autonomy or medical, and that's because you need to have a lot of data to inform the generative algorithms to be specific enough around the type of diversity and the nature of imagery that you want to get out. And we are a horizontal platform and intentionally don't have that deep specialty in just one domain. That's one thing that's going to change. It may seem like a tired old theme, but it is amazing actually to see what some of the open standards activity, how it's converging these days. I think that, Nadine and OGC have done a tremendous job over the last few years at kind of changing the persona of open standards to be more like a shepherd than a dictator. And that's really opened up a tremendous amount of collaboration around major companies like Epic Games and Nvidia and others, and then smaller companies who are also major in their own way, like Cesium and others. And so what we're seeing is this really interesting convergence of reality capture, game technology, rendering, and even human modeling, and all kinds of other things that are really creating the opportunity for kind of an open playground of capability on top of which you could do all kinds of things, including build synthetic data pipelines and all kinds of things. So I think that open standards move is very interesting. I personally will be really interested to see how USD ends up somehow blending with the web. Right now, there's a huge disconnect between streamable 3D on the web and what USD is, in my understanding. I think USD is also just at the really early stages of being able to serve geospatial content. For any of your listeners who don't know what USD is, it's kind of a dynamic cache format that is now kind of an open interchange for 3D information for, in some cases, extremely large scenes. It was originally built for films, which can have a massive, gigabytes, petabytes of 3D content and 2D content used to render highly detailed film scenes. And over time, that has been adapted to additional workflows around gaming and simulation and other things. Like I said, it's just started. I saw the preliminary attempt at geospatial in USD. I think that came out last year, was really early. That's going to keep going. And then I'm really interested to see how that influences or merges with the web. You've got a whole set of different technologies with I3S, which I was involved with, and then 3D tiles through OGC for streaming geospatial information on the web. So that's a really deeply techy, nerdy thing, but it's an interesting area that will kind of bring things together down the road.
Wow, that is a lot to think about. I'm gonna have to go back and listen to this last section of the podcast quite a few times, I think, to really get a handle on everything that you just mentioned there. But I really appreciate it. I think probably here's a great place to sort of wrap up the conversation as well. And I want to say that I really appreciate your time. This is a complicated subject, and I think you've done a great job of explaining it to me. I'm hopeful and confident that the listeners also have got a lot out of this, so I appreciate it. We've mentioned the name of your company a few times, but let's clarify it for the listeners one more time. Where can people go if they want to reach out to you, or if they want to find out more about the work that you're doing?
Sure. And Dan, thank you very much for the opportunity to chat with you. It's been fantastic. I'm Chris Andrews. I work with rendered.ai. You can find us on the web at rendered.ai, and we have a trial that people can actually sign up for right on our website. We have quite a few videos and a kind of explanatory recorded webinars about synthetic data. And what users can really kind of think about is essentially if you're relying on real sensor data to train your algorithms, it's not going to be affordable or possible in many cases to acquire all the real sensor data that you would want to build out your business case or business model with AI. And rendered AI can be used to generate essentially fake, fully labeled computer vision content for training a variety of computer vision algorithms. And in that fake data, you can actually design in all the diversity that you might want to try to address the business problems you're tackling. And it's a fun area. It touches everything from messes on carpet to satellite data collection to real hardcore use cases of emergency medical, vehicle damage, all kinds of stuff. So it's a great area to be in, and it really does apply broadly across computer vision.
Thanks again, Chris. Really appreciate it. I can see a lot of people trying this out. It seems to me that it's almost impossible to imagine a future without this when we think about computer vision. So again, really appreciate your time. Thanks very much.
All right. Thank you, Dan.
I really hope you enjoyed that episode with Chris, COO and Head of Product at Rendered AI, and I hope this has helped you understand a little bit more about this idea of synthetic data. I mentioned at the start of the episode that this is building on top of other podcasts that we've published previously, and there'll be links to those in the show notes today. A couple that you might find particularly interesting are the following. So, computer vision and GeoAI. So this is a comparison between the two. They're not exactly the same thing, and it's probably worth understanding this. There's an episode called Labels Matter. So this dives into the idea of annotating images and how that happens today and the process that's involved if we're doing it manually. And some time ago, I published an episode around fake satellite imagery. And I think I mentioned it in this episode that you've just listened to. So this was the idea of using GANs, so generative adversarial networks, to create fake satellite imagery. So I think those two would be a really good start, but if I find other episodes I think that you might find interesting, I'll include those in the show notes, so please check them out. Again, thank you to the Open Geospatial Consortium for helping make this episode possible. Really appreciate your support. And that's it for me. I'll be back again next week. I hope that you'll take the time to join me then. Bye.